thanks for the very long introduction. I don't think that needs to be that long because we more or less know each other for quite some time, right? So yeah, as I said, my main purpose of coming to Japan was for my personal fun, but because we are doing very similar things, I thought that it might be interesting to tell you what we've been working on for these days. And well, the preprint is not there yet, but we expect to upload that pretty soon, maybe in the next few weeks. Okay, so if you're interested, you can later on check the preprints. But essentially, today I'm going to talk about something that is very exciting, we think, but also quite different from what I've been doing previously. Okay, and this is a work done by my amazing PhD students. So Sharon, Jacob, Filippo, and Wano visited here last year together with you, right? And the idea here is you still want to do alternative quantification and especially alternative composition, and we want to do that with this language model in context learning. So as a quick peek of the results, right, I'm just showing you some interesting visualizations. There is no quantitative result yet, but I'm just telling you that these results are generated by purely prompting language models. Okay, so and I want to tell you essentially how we've been doing that. Okay, we are all very familiar with Bayes' rule, I hope. Okay, this is just to remind you, right, that in Bayesian world, right, so we want to model our underlying parameters or some kind of underlying latent variables as random variables, put priors on that, and based on the observation of the data, we will update our prior belief to posterior belief, and then use the posterior belief later for our new task. Oh, okay, then nowadays, language model has been already very, very popular. I don't need to mention it more, but there has been very different kind of research and applications within the language modeling field, right? So pre-training is something that mostly the big companies can do, right? That you will train this very big neural network with WebCL data. And then once they've trained that, they might open source online, right? And then we as researchers can fine tune them or do sometimes they post training work to steer them towards these domain specific data and applications. Okay, so those are things that we can still do. Nowadays, people also try to do something without fine tuning or changing the parameters of your neural network, which is this thing called test time scaling. Okay, there are a lot of things of them. So the interesting question here is that what can Bayesian people do within these three stages of the pipelines, right? So, well, obviously the first stage is pre-training is very hard. I think this slide is already outdated because the latest one actually comes from your lab, right? But at least 3 years ago, people have already tried to see whether you can push Bayesian inference method or approximate Bayesian inference methods to neural networks of millions or billions of parameters. I think my observation here is that if you can run Bayesian inference on these big neural networks, this result actually shows you that you can do better than just a point estimate, which is, I think, this sort of thing at that time in red. But the problem here is that the computation cost is just way too high. Especially, you can also need to run these multiple forward passes, that i.e. Monte Carlo sampling, in test time. So I think that apart from this kind of innovation on this statistical side, to make Bayesian methods somehow progress more on this pre-training end, you also need to develop this high performance computing and also MLC's type of work. Otherwise, I think this is a dead end. Okay.
Could you explain a little bit?
Yes, so this is actually the work done by Dustin Tran and people at Google 3 years ago, right? So they actually tried, I think, some kind of deep ensemble mixed with Gaussian component, okay? Kind of like what you've done in this approximate inference challenge.
Was this with flip out and stuff like that?
I don't think this is flip out. I think I think they really use some ensemble methods, okay? And they want to show whether, by training these kind of ensemble methods, right, and test that on various different tasks, okay, whether they can actually perform better than, let's say, specialized models, point estimate for each of them, okay? Yeah, so Well, this is not the not my work and also not the point of today's talk. I'm just trying to tell you that what is the status right now. Okay, I hope you guys can push further. Okay, so the other thing is about fine-tuning, right? So, well, one of the most popular fine-tuning methods nowadays is this thing called low-rank adaptation method, or LoRA for short, right? So the idea here is you fix the original weight matrix, but then you add a side pathway, where this side pathway is characterized by this kind of weight matrix of low rank structure. You can choose this rank R to determine how parameter efficient you are for this fine-tuning procedure. Okay, so LoRA has been like the standard fine-tuning methods right now for language models, and obviously you can also do basic methods on that. And since this kind of Imperial work from Lawrence Hutchinson, okay, all these kind of methods like Laplace, version inference, deep ensemble, SGM, sensing, all these methods has been tried. Okay, I haven't listed out the references, but I guarantee that all of them has been tried. Okay, so yeah, so one of my PhD students, Shavindra, right, first of this paper, we are also trying to do some kind of fine tuning for language model, but in this chemistry context, and we did find that doing some kind of uncertainty quantification in the fine tuning procedure will be useful for this downstream task. So this part is still worth doing, okay, but if you talk about methodology, all of them has been done. Okay.
Was this worth doing?
Yes, I think so. Yeah. Okay. So the
Don't show a similar kind of graph.
yeah, because that is, I mean, the problem here is I'm going to talk about the third one. Okay, that's the today's talk. Okay. So yeah, so we want to talk about the third problem, or the third kind of paradigm that people are currently trying to research on language models, which is this text time scaling. And in particular, I'm going to talk about in-context learning. Okay, so ChatGPT says in-context learning is a phenomenon observed in LLMs where the model can adapt to a new task simply by being provided with examples or instructions within the prompt without requiring any changes to its underlying parameters. Right, so this is actually quite nice for practitioners that you don't need to have a very deep GPUs to tune the parameters. You just need to have some kind of consumer grade GPUs that can serve these low precision language models, and you're trying to do something by a prompt. But then what exactly is this is doing, right? So if you really think about what language model is doing, at least autoregressive language model. So autoregressive language model actually defines a sequence of conditional distributions. Okay, so you give some tokens as input, and then the language model will tell you what is the distribution of the next token. Okay, and actually you can use arbitrary number of tokens, and that's basically what we meant by this language model as a set of conditional distributions. Okay, now let's think about how you can actually use this language model to do some kind of data science task. Let's say you have a supervised learning data set of X5 pairs. Okay, naturally speaking, one way to do that is you can put in the X, the input, tokenize them as the all the tokens, and then tokenize the Y in output as the even tokens. And then you arrange your data set in such a way, right, that you have X1, Y1, X2, Y2, etc. And then in test time, whenever you want to actually query a new test input answer, X star, you make X star to be the 2n plus 1 token. And then you ask the language model to predict the next token, and hopefully the 2n plus 2 token will be the answer that you want. Okay, I hope this setup is clear. In practice, we are doing something more complicated, but I want to talk about the framework within this notation. Okay. So why this is interesting? Well, I think I want to go back to essentially, close to 100 years ago about this motivation of doing Bayesian inference. Okay, so around 100 years ago, so Bruno Davinetti, okay, so he was Italian, okay, so he proved some very interesting theorem called definition theorem, okay. So it says if you can construct a joint distribution of your outputs, basically y1 to yn, even all the input x1 to xn, such that this distribution is invariant to permutations. Okay, so this is something called exchangeability. Then there exists a underlying Bayesian model with some latent parameter theta. We don't necessarily know what it is, but it exists. Okay, so you can put this model will have a prior over this latent parameter theta and some likelihood term there, and the joint distribution there or the marginal distribution here will be the marginal likelihood of the Bayesian model. Okay, so this is a very classical result, and I think one of the very nice things to note about this result is because of this existence of this mixture model, right? So it later on motivated this kind of explicit Bayesian modeling setup that tells you, okay, if you want to model the joint distribution of your data, then you can actually start from the Bayesian modeling of having some assumption about what is your underlying parameter, what is your prior, what is your likelihood, and do this Bayesian inference stuff. I think this is one of the key contributions from this theorem. Okay, but we are not going to talk about this until maybe a few minutes later. Okay, so now let's assume that we are in this explicit Bayesian modeling setup, which means we do have a explicit Bayesian model of some parameter theta. We have some posterior of that, and then we can do predictions, right? So the predicting posterior here, P of y star given x star and d, is computed by basically you sample all possible theta from posterior. For each of the theta, you compute your prediction and then you average over it. Okay, so this orange equation is the posterior predictive. Okay, so what we can do, what can we do with this prediction distribution, right? So, well, obviously we can compute uncertainty, and if we are going to use this entropic metric for uncertainty, then we can compute essentially the entropy of the prediction distribution. This is something called total uncertainty. But at the same time, you can also do some decomposition to get to the aleatory uncertainty, which is due to the inherent stochasticity in the data. And we can also have this epistemic uncertainty, well, which is due to the lack of the data. Okay, so I hope you are familiar with this concept, but we can maybe say a little bit more about it. So what do these two different concepts mean, right? Okay, so why are we interested in computing aleatory uncertainty? Because we are interested in understanding the inherent randomness in data. So let's assume that there is no model error, which means you believe in your model, right? So that means there exists an underlying ground truth parameter theta star that matches with your data distribution. Okay, so then if we want to understand the randomness in the data distribution, then we can use some kind of randomness metric, in this case entropy, right, to compute the true aleatory uncertainty of this data distribution. Okay, but the problem here is that in practice we only have finite amount of data. Right, we never know what theta star is until we have an infinite amount of data. So then the previous definition of aleatory uncertainty is actually a Bayesian estimate of it, right? You compute essentially the entropy for each possible theta from the posterior, and then you average over the posterior. Okay, so this estimate will converge to the true aleatory uncertainty when, well, first, the model is identifiable, which means you believe in your model and the ground truth there exists a theta star, and second, the data amount of data goes to infinity. Okay, so the second term is the epistemic uncertainty, and it is defined in mutual information if we're using entropic metrics. So there are two ways to interpret mutual information by writing its two definitions. So one way to write it is essentially writing it as the expected KL, but with theta as your random variable argument. Okay, so this is basically saying that, okay, so given the data set, well, what is the amount of information gain I can get by adding one more data point, x star and y star? Okay, right? So if this is very informative, right, then essentially your posterior will change a lot when you add in this single data point, so that KL averages will become big. Okay, so this is the idea of expected information gain. And this expected information gain idea has motivated kind of applications like active learning and data organization. Well, obviously, you also write the mutual information in a different way, right? By taking your y star as your random variable argument. Okay, so this is basically asking, okay, what is the amount of disagreement between the experts theta sample from your posterior? Okay, if your theta parameter sample from the posterior give you very different predictions, then this KR divergence is also high. Okay, so this is telling you disagreement between experts in posterior, and people also use these concepts to perform things like out of distribution detection or adversarial example detection and other kind of detection type task. Okay, so entropy is just one way of quantifying uncertainty. You can also do it with variance, and the way you can also decompose the total variance to the editorial variance and the epistemic variance. It is very simple. It's just the law of total variance. Okay. I hope this is clear. Okay.
Can I?
Yes.
No. Yeah. I don't know how important it is for your talk, so
Yeah. Okay.
feel free to not like get into it if it's not important. I was just thinking the extensibility stuff. Is it? From what I remember, I think the statement is that there exists a latent verbal form, right? Okay. I see. So then this theta star thing that you did in the previous slide, it's like, why are you doing that is what I didn't. Is it just to give people an insight, or
just give people the insight what
Okay.
What does editorial uncertainty mean and what does epistemic uncertainty mean? It has nothing to do with what we are going to talk about.
Okay, so like there is a danger here, right? That when we fix a model or make some assumption, then it's up to what we did, right?
Yes.
So okay.
Yes. Okay. So maybe something that would be interesting is the following, right? So the finite theorem tells you there exists a underlying latent parameter theta for that, right? The problem here is that whenever we start to do the modeling with explicit Bayesian inference, right? Then we need to actually start to think about what exactly is that theta? What is the dimensionality of it? What is the domain of it, right? And then this starting from that, you already have the risk of making some model error, right? So yeah, so that is the kind of risky part. But I'm just saying that the few slides tell you that, okay, if you assume you have no model error, which is a big if, then how to interpret the decomposition that I just presented.
Like this, my
My point was that like in the language model there is no theta, it seems, at least the way that. Sorry, maybe I'm jumping ahead from this. So I'm just trying to keep in my mind that this split depends on the definition, right?
Yes.
And just because if we don't talk about the definition doesn't mean that we have kind of solved that problem, right?
You will see that later. Okay.
All right.
Yeah, I think this is actually a very interesting part. Okay. Now, the interesting thing here is let's go back to the language model setup, right? So we just know that language model parameterize a set of conditional distributions. Okay. We actually don't know whether the finite theorem actually holds. Even if it holds, we actually don't know what is the parameter theta. Okay, right? So it is actually an unknown. It's not like, oh, you know the form, but you have no traceability of the distribution. It's actually you actually don't know the form either. Okay, right? So this basically says, okay, imagine I still want to somehow compute this kind of decomposition for this unknown, right? So many of the existing Bayesian deep learning methods cannot work because most of these methods need to first assume you are in an explicit Bayesian modeling setup, which means you already know what is the theta. what is the procedure for, at least up to a normalizing constant, you do some approximation directly to the procedure distribution P of theta given D. Okay, and then later on you do this Monte Carlo from the Q distribution. Okay, we are not in that setup. Okay, so what I'm going to talk about today is there is still a way to approximately compute this condition without actually knowing explicitly what is the theta. You just need to somehow assume it exists. Okay, so that's the interesting part. Okay, so let's dive into it. So the idea is actually very simple.
One quick question for this implicitly defined model, we needed the exchangeability on, but I don't see how for the LLM it's like autoregressive, so how can it be exchangeable if
You will see that later.
Okay.
Okay, so at this moment, let's just assume that you do have an implicit Bayesian model. It can be explicit or implicit, but at least there is a Bayesian model. Okay, so we can construct a versional estimator in this way. So imagine the actual question you want to ask is this X star. You want to know the answer X, Y star of X star. Okay, before you ask this X star question, you need to pick a auxiliary question, or we also call it probing question Z. Okay, you need to ask the model to provide its answer, okay, to this question together with its context D, which means we are trying to compute this distribution P of U given Z and D. Okay, so because we can the language model can give you autoregressive predictions, then this thing we can compute it. Okay. Then we can compute the following estimate as our aleatory entropy estimate. It is still very similar to the previous kind of definition, right? You still compute the entropy of something and then average over something. But here it is actually compute the entropy of the language model's answer to the real question after seeing the data sets as well as the dreamed answer to your auxiliary question. Okay, so that is the key. And then you are going to average over possible dream answers to your auxiliary questions. Okay, so the interesting thing here is that you can show that this estimate is a upper bound to the previous definition of the aleatory entropy. Okay, so if you want me to remind you what is the previous definition, then okay, so this is the previous definition, classical one that you often see in many of the Bayesian deep learning papers if they compute the transitions. Okay, and we can actually also show you what is the gap between this version estimate and the underlying kind of Bayesian estimate of the aleatory entropy you want to get. Okay.
Sorry, so
I guess this is an important slide.
Okay, yeah.
Stopping here and asking a question. So what is theta in that one? Or like I don't understand. So you put theta there, but you were trying to avoid it. So that's why
Yes.
it's been dashed.
Yes. Yes. Okay.
Then you're saying upper bound to something.
Yes.
You think that I'm not going to talk about.
No, I'm not trying to avoid that thing. Okay, I'm just trying to say, okay, so I do have a Bayesian model, either explicit or implicit, but I don't want to compute the decomposition
So
by.
you assume the Bayesian model.
Yes, I already assume the Bayesian
So
model.
you think the theta is there.
So theta is there, but I just don't need to compute it. Okay, I don't need to access it. I don't even need to know what's the form of it.
Okay.
You just need to assume it exists.
Okay.
Okay.
And I suppose that you're saying that U and Y star, they would both be computed from it because it's the same LLM. Is that?
Yeah, that's the same LLM. It needs to be the same LLM.
Okay. But
Okay.
it's possible that U and Z is like completely weird things.
Yeah, it
That
could
have
be.
nothing to do with Y star and X star.
Yes, correct.
Okay, and then you're saying the upper bound is really bad. Is that what you're saying?
Well, okay, so I can tell you the next slide, right? So the interesting thing here is that, this bound is true for any Z. Then, that the version inference people love optimizing bounds, right? So because this bound is actually true for any Z, then you can actually try to minimize this upper bound by searching optimal Z.
Yeah, makes sense.
Yeah, right. So let's assume you can
I
do
mean,
it.
it makes sense to me to say like, let's ask a question that's relevant to X star and Y star and figure out, you know, from that point of view, it makes sense.
Okay.
You know?
Yeah.
So you've written it mathematically, so it makes sense. Also,
Yes.
I guess.
Okay, yeah, but the funny thing here is that really, and I mean, so we are asking, questions in the same domain as X, which means, I mean, in our experiment, we use Z in the same domain as X, but in principle, you don't need to do that. Okay, so let's assume you can optimize that. I will talk about how you optimize that later. Okay, then you've got hopefully good upper bound to the uncertainty. The total one is just using the autoregressive distribution. You can compute it already. Then it means that you just use this decomposition rule, total equals to aleatory plus epistemic, right? Then you can actually get back to the epistemic uncertainty estimate, also in a virtual form, and this means you have a lower bound to the epistemic uncertainty. Okay. So I guess the burning question here is why this upper bound is true. So that there are two types of proofs. I'm going to talk about only one of them, but that one is very, very simple, which is the 101 thing for information theory data processing equality. Okay, so you can see what we've been doing here. Okay, right? So the idea for this Bayesian modeling here is that whenever you want to do a prediction, right, you need to go through the underlying latent parameter theta. Okay, so this means, I mean, you ask, let's say this new question Z, you want to get this view, right? So it means that this theta tells you how to generate U. Similarly, this theta, when you answer the real question X star, tells you how to generate Y star, right? And this means we have constructed this kind of Markov chain structure, okay, of this co-computation procedure. Remember that the definition of epistemic uncertainty is actually mutual information. The data complexity inequality tells you that the mutual information between Y star and theta is always bigger than the mutual information between Y star and U. And the mutual information between Y star and U is actually our variational estimate. You can show that. Okay, so this is a super simple proof. Okay, so any questions regarding this?
You mean that given the arrangement, the can use like one opting from the one pusher from the theta, so you mean the rate operation wise high more relevant to the relevant to the Y star, so you mean there's many appendix information gain between Y star and news less than on the information
it's not working.
Well, okay, so mutual information is in fact just trying to compute how dependent two different variables are, right? So data processing inequality tells you that the mutual information Y star between Y star and theta should be bigger than the other one. The reason here is you can think of U as a noisy measurement of theta. Okay, right? By pinning down U, you are not exactly pinning down the correct or kind of precise value of theta, which means there is still some randomness, right? Then we're trying to talk about essentially like the dependencies, right, from the Y variable, right? So obviously Y variable depends on theta, but then U is a noisy estimate, in some sense noisy estimate or noisy measurement in anyway, okay, of theta, so that U contains some information about theta, but not all of them. So that explains why you have this inequality.
I mean, mathematically it makes sense. It's fine.
Yeah.
But I think the more interesting question is the other way.
Okay.
When is this really bad?
Okay.
Because you're asking arbitrary questions.
Yes, we are asking arbitrary questions.
And so you can always do experiments where you say that you can start with some Y star, X star, and then change them and construct U and Z. That'll be an easier case. But I'm trying to think like most of the questions will be unrelated to X star and Y star, right?
Yeah, and that's basically why we need to actually optimize Z.
But that's why like then it's optimization is kind of then it
went into the wild, right? I
Well,
mean, what the reason why
Okay.
we have theta at first place
yeah,
is because we could actually pin this down to
Yes.
an extent, right?
yes,
And then you said, okay, let's get rid of theta. Then you back to that place
yes,
where you're in the wild.
yes,
You have everything in there.
yes.
So I understand as much
Uh-huh.
and I appreciate the math as well and the thought and all that, right? But like, how are you say optimize it, right? But I think we need a little bit more control.
Yeah, I totally agree, right?
And
I'm not
some
trying
more
to,
theory there would be great.
so I'm not trying to suggest that, oh, if you already have a explicit Bayesian model, which means you have already have control to theta, you should use this method. No, I'm not suggesting that. The reason why we are interested in deriving this method is in the language model setup, we can construct a setting to tell you theta exists, but we cannot access to theta. Okay? So in that setting, I'm still interested in computing uncertainty decomposition. I can show you some interesting application later. So that's basically that motivates why we develop this framework. And yeah, so I totally agree with you that in principle, the search space of Z can be super big, right? So we actually developed some practical algorithms to narrow down the search space. Okay, yeah. So maybe before we talk about the algorithm, right? So I also want to say a bit about how to interpret the gap. Okay, right? So the gap between the variation estimate and the underlying kind of exact one is some kind of mutual information again, or the expected mutual information. Okay, there are again two ways to understand that based on the two definition of mutual information. Okay. The first one is you can still write it down as the KL using the KL divergence between the distribution over theta. Theta here is implicit. Okay, so the way you can think about it is how much information gain can I get from knowing Y star? Okay, based on one further kind of question. Okay, right? So this is the what we call residual information gain in fantasy, okay? Because U is not coming from some external label. U comes from your language model's own dreams, okay? So the other way is again you write the KL averages with Y star as the random variable, okay? So this says what is the remaining amount of disagreement in predicting Y star, given that I have also dreamed the answer to my auxiliary question Z. Okay, so yeah, so this is the way you can interpret the gap. Any questions so far?
Well, these quantities were equal in the previous slide somewhere, right?
Yeah, they are equal to the quantity in the previous. I just tell you how you can interpret this gap.
Oh, so they're still equal in this one?
Which one? What do
Like
you?
the blue and the orange, they're equal.
Yeah, they're the same.
There's-
So yeah, they are all this mutual information. I just write down two definitions of the mutual information to tell you how to interpret this thing. Okay? Yeah? Okay? So so far so good. They are all very interesting mathematical frameworks. Now the interesting question here is how to bring that to practice, right? So the very first question that you want to answer, which is also asked by Thomas, is actually whether language model really do Bayesian inference. Okay? Right? So I think there has been quite some debate on that, right? Because first of all, when people look at this in-context learning as constructing a sequence of conditional distributions, they feel like, oh, it looks like marginal distribution, right? Or marginal likelihood, so that it's natural to think they are doing Bayesian inference. But Chris Tom's group, right? They put that in the test and say, okay, so one thing that you want a Bayesian inference procedure to satisfy is this thing called martingale property, which says, oh, if I'm going to answer a probing question first and then come back and answer my real question, the distribution of the answers to my real question should not change, right? In other words, fantasized future data should not change current prediction. Okay, so they tried some experiment. I think some trying to estimate this posterior probability of these coin flip probabilities using this LM dream data. Okay, I'm actually not exactly sure what this plot is, but they show this as an example to show, okay, if you satisfy linear property, then your estimate by increasing number of drift data should be just like flat estimate there, but you see some kind of drifting away pattern. So at least this paper, they try some simple experiments, right, to say that empirically speaking, language model is not doing Bayesian inference, especially when you let it sort of like do sequential predictions for longer and longer. You would start to drift away from the Bayesian paradigm.
This was in the in context?
Yes, that's in context. Yeah. Okay. Another interesting question is here, is that should we give up, right? So I think the answer is yes and no. So yes, you should give up. In terms of thinking about just simply doing next token prediction with language model as Bayesian inference, at least with current open source models. But no, in the sense that you don't necessarily need to just do one shot prompting as a way to construct a Bayesian machine. You can think about a prompting language model as part of the pipeline. You just need to somehow make a pipeline so that at the end of the day, that pipeline is doing Bayesian inference or approximate Bayesian inference, then that's okay. Okay, I hope this answers your question. Okay. So then we can talk about how we are going to construct a approximately Bayesian procedure, okay, by prompting language models. Okay, so, well, there are at least two necessary conditions, okay, that you need to satisfy if you want to do Bayesian inference, or in other words, if you want to promote exchangeability. Okay. So, well, obviously, the first one is permutation invariance, which says if you're going to permute your in-context data in however ways, right, then your prediction to the next question, right, should not change in distribution. Okay. So, our approach of doing that is basically just to do ensemble with permuted context. Okay, this is our computational way to approximately satisfy permutation invariance. The approximation comes from the computation budget, right? Obviously, if you increase L, then you can get closer and closer to a permutation invariant prediction procedure. Okay, so the second one is the martingale property that we mentioned before, right? Fantasized predictions should not change. Fantasized future should not change the current prediction. So what this C2 condition means is, if you're going to basically use the ensemble prediction by first answering, right, the probing question, and then based on the probing question's answer the real question, average over all possible answers, right? So this is the one way you can construct a prediction. The other way you can construct a prediction is just simply ask the language model to answer the question directly. Martingale property says these two distributions should be equal. Okay? So our way to ensure this, or approximately ensure this, is to restrict your search space of these three questions. Okay? So we are going to define some search space later.
Sorry, it says, why is it equal? There's no Z, so does this happen?
Sorry, so
Like in the left-hand side, there's Z, and the right-hand side, there's no Z.
the right-hand side here just says you directly answer the real question.
Equal.
No, so this one is something that you want to ensure.
Ah, okay.
It's not by definition.
Oh, I see.
This is something that you want to ensure, and that's basically why we do this kind of thing. Yes.
For this permuted context, doesn't it somehow destroy the meaning? Like if the context is the cat is on the table, and then I permuted, I have something the table is on the cat, and then I average, then it loses.
You look at how we actually do the permutation. So the permutation will keep take X and Y pairs. You are permuting pairs. You're not doing any random permutations. Depending on how you actually, so the funny thing about exchangeability and the validity theory is, depending on how you define the exchangeability on which level, the underlying Bayesian model will be different.
Can you give an example? I don't understand
Yes.
how the permutation works. Like,
So imagine, let's say you want to classify cats and dogs. Okay, right. So let's say cat has label 0, while the cat a dog has label 1, right? And you have a data set of 10 data points. Okay, then you can permute basically x1, y1 together, swap that with x3, y3. Okay, but you still need to ensure that the cat is labeled as 0 and the dog needs to be labeled as 1.
But this is like image classification, and here it's like auto-regressive LLM, but it doesn't make a difference. Or...
Yeah, it does not make a difference. It just depends on how you tokenize things, right? I already mentioned that you are going to tokenize the alt token with X and even token with Y. You need to ensure that this is still the case when you do the computation.
Like model is trained in, I mean, I think I understand mathematically and I agree with you. But then I also am thinking, because the model is trained in a weird way, right?
Yes.
So then you're constructing it on top of it in this way.
Yes.
It's not, we're not sure.
Yes. So okay. So one thing I need to say that is we are not changing the total obscenity, or in other words, we don't have explicit control in terms of the quality of the classifier. This is unlike the explicit kind of a training case, right? Or explicit basic modeling case that you do your nice algorithms like, IVO, perhaps, to train your neural network, then you have some good control of the accuracy. Here, no. Okay? I'm just telling you that you can construct a classifier in this way and compute the conversation. However, how to improve the classifier's accuracy, that is still a very interesting research question.
Actually, this one right to ensure like computation layers, actually some neural process like equal some like different structures so that their network is designed in the to preserve this condition. So in this case, is it not possible to design architecture? I mean, this is just to me.
So neural process, right? So neural process, especially things that with this set architecture, right? They explicitly ensure this happens. They don't need to do ensemble, right? Because they process each of the points first, and then they do the aggregation, and this aggregation part will ensure the computation invariance.
Yeah, I think this like appreciate the aggregation design in ensemble with the episode and then they link the like aggregation part.
Yeah. Yeah, I mean, so I'm not saying that neural process cannot work. In fact, neural process, if you use neural process, you don't need to do this first one. I'm just telling you that I'm going to use an off-the-shelf language model. Let's say I take any language model from the Honey Bakes market right now. Okay, but those of models, they are not trained in a deep set way, right? You have no guarantee in that sense.
I'm sorry, I got it wrong. So I'm not well versed with these methods. But the underlying assumption here is that we can set up this pipeline on instead of explicitly modeling theta, we can explicitly model on the in context data and U and C.
Yes.
Now, in order to satisfy the martingale property, we are restricting the solution space in such a manner that KL is less than epsilon?
Yes. So we will need to actually define the search space of Z and then do some kind of filtering process such that the remaining solution that you're going to collect will satisfy this quantity.
But won't that induce a very sharp trade-off, because this is a very sharp constraint in terms of restricting.
Yeah. Yes, indeed.
Right, yeah.
Okay.
I mean, I was just actually thinking about inference stuff in the beginning when you were writing these things, because if I want to think about what Z and U I should add the ones that are very related to it. Right?
Yes, yes, yes.
But then like here you write equal, and that kind of, is a bit.
Well, this is not, we are okay. Let me just clarify again. C2 is not trying to say it is defined to be equal. We want to enforce them to be equal or approximately equal.
Similar.
Yeah. Okay.
I think if you didn't have C2 and you just said to me that, I mean, a very simple thing to do is just go in the training data and look for things that are similar. and
Yeah.
Construct answers based on that.
Yeah.
And I think people would do that, you know. That's
Yeah, you can,
without even-
indeed. Okay. I guess one of the interesting reasons why I want to say this here is that you can definitely follow your intuition, right? But mathematically speaking, how good that estimator is, right? It is possible that language model is doing some very weird things so that the question that you think is sensible to ask, they actually don't satisfy, let's say, these properties, right? Okay. Okay, so now let's talk about essentially the whole pipeline. Okay, before we talk about how we search Z. Okay, so we need to first have a set of candidates. I'm going to talk about it later. Okay, so then you basically ask this language model every single Z questions we put here in the candidate set to get its dream answer. Based on the dream answer, and actually you need to actually collect multiple of them. You need to then answer the real question. Okay, to essentially get the prediction here, step 3, right? And then step 4, we can compute essentially all these rational quantities we are interested in. Step 5, we are going to filter out those, we call it non-Bayesian Z, which means those ones that does not satisfy this approximate martingale property, right? And then for the remaining questions, we're going to compute the minimum entropy because we are constructing a variation upper bound to the electoral uncertainty. So this is the pipeline. It is expensive, but it is doable. Now the interesting question here is how you're going to choose the Z candidate. Okay, we have several options, right? Obviously, the ninth one would be to just pick random. Okay, and you can also ask similar question as you said, right? You define some kind of neighborhood. You can define it yourself. You perturb your X star, the real question within a neighborhood to get your candidate answers. You can actually even repeat the question. Okay. We also try a very sophisticated method to just see how it works. Okay. So interestingly, why you can actually ask the question again, that there is some kind of interesting math behind it. Okay. Again, as I said, right? So this Gaussian process regression example there, you already have the explicit model. I'm not suggesting you to use our method to compute that, but I'm just using this example to tell you to analyze, what would happen if you just repeat the question. Okay. So at the end of the day, you can work out that in GP regression setup, if you repeat the question, then your electoral uncertainty estimate is, well, for sure, upper bound, and then the gap is quantified by this term. So if you're familiar with GPs, then this term should be very familiar to you. Okay, we know that this term is approximately 0 when your X star is close to the training data point. I mean, at that point, you are basically like quite certain anyway, right? But this term can be big when X star is far away from your data point, which means your gap will also become big, right? So this analysis is interesting because it tells you, okay, you can indeed repeat the question again, but depending on your actual questions, well, whether it is in distribution or out of distribution, repeating the same question might be or might not be a good idea. Okay.
Sorry, see this GP regression, you are saying that you're modeling GP regression through MLM, or
no? So no.
This is a separate thing.
Yeah, this is just a analytic example, right? This is just a thought experiment. Okay, you just assume that your underlying basic model is a GP. I'm not suggesting you to use our method in that setup. It's just a thought experiment.
Yeah.
Okay. So okay.
It depends on like what your training data you have and what kind of kernel you use, right?
Yeah.
Because you may not be penalized for doing the same data if you have lots of correlations inside.
Yeah, but I think this point, I think the main point is to tell you the quality of this procedure by repeating the same question really depends on whether your real question is in distribution or out of distribution. Imagine that your in context kind of data or kind of results are like let's say primary school math, and then your real question X star is, let's say, university level math, right? So those are very different questions, and perhaps asking the same question again might not help because your context is just primary school math. right? So this can be another interesting way to interpret this result. Okay, so yeah, so this is actually how we actually from the language model. It's slightly different from what I said about putting the odd token as x and even token as y, but you can make a format that is consistent everywhere within your within your experiment. Okay. And we just, when you're actually going to do our method, right? You just pick the particular question, you append this question to the context before the last line, and then you run your approach and on appending the U variables. Okay, so this is essentially the first page result I show you, and this result is obtained using the presenting method by prompting this language model Quen 2.5 40 billion parameters. Okay, there is no analytic ground truth. There is, it's very difficult to quantify in a quantitative way whether this is accurate or not. I just want to show you essentially the qualitative behavior. And the qualitative behavior looks about right in terms of expectation.
But couldn't you do like you create data, synthetic data from a model that you know, and then you ask the language model about it, and then you want to get us, as you ask more questions,
we can.
These uncertainties to kind of reduce in the same way.
Yes, we have one example for that. Okay. So, but also just to tell you that, okay, so you can also work on slightly more challenging data. Okay, so this is the 3-class spiral classification data, and the first panel A, just tells you the classification results. Okay, so it is well doing decently. I'm not going to say it's super accurate in terms of prediction, but it's doing okay, right? So you can also show some kind of decomposition result here. Okay, we can also try regression. Okay, so this regression example is very interesting in the sense that it has this heterostochastic noise, right? So you have this left-hand side observation in purple that is mostly like noiseless, but the right-hand side observation, you have some noise there, right? So if you look at the decomposition result here, where the blue curve shows the total uncertainty and the pink curve is auditory and the gap, okay, between them is actually the epistemic one. Okay. So first of all, if you look at essentially close to the observations, so the observation is shown in this vertical dash lines. You can see the uncertainty is actually going down, and you have this increased uncertainty in between. But the interesting thing here is that you can also see the additional uncertainty here on the right-hand side higher than the left-hand side. Okay, I was very amazed by this example when my PhD student showed me this figure. Wow, prompting a language model in a certain way can actually see this kind of results. I was very amazed.
The thing in between going up, both of them are going up.
Yes. So we have no ground truth, right? So in this case, we can.
Here is ground truth. I haven't.
Okay.
Just looking at it, right? Like my aleatoric uncertainty. I'm also a language model, I guess.
Yeah.
So there, I don't feel like that the uncertainty should go up, right? It's like at least, like I know quite precisely how things are going, right? So it doesn't seem like that it should go, at least not both of them.
Yeah. Okay. That's fair, right? I think what I can say here is that these days prompting language model is not very precise control in terms of model behavior compared to just to explicit model training. Okay, I think this is close to the best we can get. Maybe we haven't got the right kind of prompting technique. Okay, we are definitely actively investigating on that. Because what we are proposing here is just to tell you, you give me a Bayesian procedure. We tell you how to decompose things, right? But how to construct that Bayesian procedure in a way such that the classification or prediction accuracy is high, total uncertainty behavior is correct. So how to do that? That is still an open question.
But it is quite nice in this example because, as I was saying, that you think about U and Z, right? Think about U and Z. They are like if you pick a question in between that region where you haven't observed anything, your model is actually telling you that it's not going to change that much, right?
Okay.
So I'm actually surprised that your lines are really going up.
Yeah.
Something's off.
Yeah. So I mean, so I'm still quite behind compared to my PhD student in terms of how to prompt language models in a very well controlled way. Okay, I think these days, I don't think anyone knows how to precisely control the language model's behavior. Okay.
Question, so you mean that you originally expected the right side of the epistemic uncertainty almost should be same with the left one?
More or less. So I think what we want to see here for this kind of heterostratic example is because you have different amount of this noise in your observation, then you should have a different amount of kind of aleatorial uncertainty, which means in the pink curve, right? So the left-hand side, at least according to the data, should have less aleatorial uncertainty compared to the right-hand side, and this is what is showing up here. Okay, so now let's test whether this decomposition actually satisfies some kind of desirable properties of Bayesian inference. Okay, so before that, let's first talk about this classification example. So this is super simple 1D example just to show you the results, right? So we have some data points, okay, 2 classes, and you can also construct its decomposition of uncertainty estimate. I think this behavior is, qualitatively okay, in the sense that close to the decision boundary, you have high uncertainty, but mostly due to the high aleatory one. You are in this decision boundary, you are ambiguous. And when you are getting away from the observations, then you have this gap increasing. Okay. So yeah, so this is the example we're talking about. Okay, the first example here is, okay, so can we actually have this decreasing epistemic uncertainty when we have increased amount of data points? Okay, right? So the way we construct this example is the following. We are going to add more data points, but still within this region of, I think, -5 to somewhere close to 10. Okay, so it means that we are still trying to have some kind of out of distribution region. Okay, so we are only just adding new data points here. So the pen A here, we are just trying to plot essentially the epistemic uncertainty estimate, and the pen B is aleatory one. Okay, but different color is here basically shows you that, okay, whether those points are in distribution or out of distribution. Okay. So first of all, if you look at the in-distribution point, let's say it's 0 and 5, right? You can see that the epistemic uncertainty in panel A is decreasing when you have increased amount of data points. Okay. The other ones, they are also decreasing, but yeah, I guess not that sharp. I don't know. Okay. But also on the other hand, the aleatory uncertainty one, right? So it is actually flattening out. Right, so this agrees with our explanation for the intuition, right? The conditional entropy is a Bayesian estimate of the aleatory uncertainty. When you have more and more data points, it should converge to some kind of ground truth, which means it should converge to some flat kind of value. Okay.
If you have a 2D example, sorry, I mean I like this, but if you have a 2D example, you can actually, when you generate from a model, then you can compute the Bayesian posterior, right? So you have ground truth. Like if you have synthetic data, I use a model to generate it, and then I can just compute the Bayesian posterior of it, and I have ground truth.
But the problem here is that first, this language model procedure is approximately Bayesian, and this in the computational way, right? Because of this filtering process and also the permutation. And second, we have no control or very little control in terms of the language model's behavior. So even when
I thought the whole point was to estimate, like I know the ground truth in some cases, and I'm hoping that the language model can actually figure out the uncertainty.
I don't think we are talking about the same ground truth. Okay, so the variational method that we are proposing, our ground truth is the underlying Bayesian model of the LM. However, the underlying basic model of the LLM might not align with the ground truth data generation process. Indeed, this particular example, the ground truth generation process is a logistic regression example. Okay, I agree. So yeah, we don't know how to test whether the underlying ground model or the language model is actually a logistic regression model. Okay.
I mean, you give a 2D classification problem to an LLM and it can solve it, people say, right? but you actually not, right? If you actually knew the truth and then you give the data to the LLM, it spits out something and you're trying to understand how it actually knows what it knows. So the ground truth is right there, how you generated the data, right? Then you know how wrong the model is. And maybe some kind of problems it can actually tell in a right way.
Yeah.
Yeah.
I guess what you are saying here is more like this model checking model or kind of like testing whether you have whether this implicit basic model specified the language model is misspecified, right, against the ground truth.
Yeah,
More like that, right?
Some problem that you know that it actually solves quite well, and then you're trying to guess if that problem's uncertainty is estimated right. Then you would clearly kind of construct an example, which so like MNIST probably is in there somewhere, right?
I don't think it can solve any that well. No. So the current language models by in-context learning with these quantitative examples, I think they are still quite far away from solving MNIST. No. Okay. Okay. Yeah. So, well, I think we are pretty much out of time. Maybe I just show you one kind of decision example. Okay. So, multi-arm bandit. Okay. So last year, some people, well, basically Akshay, right? So we invited him for the AI stats talk, right? So they are interested in this question about can the language model play bandit or solve bandit problem in context. Okay, so what they did is essentially they just prompt the language model, telling them, okay, so previously I have tried pulling this arm, I tried pulling that arm. What are here are the reward of them. What is the next arm you are going to suggest me to pull? So this is their way of trying to solve any problem. Okay, we said no, let's not try to do that. Let's try to build a algorithm that use uncertainty estimate, but uncertainty estimate with a language model. Okay, so the setup is the following. So you have the binary reward for each of the buttons, but there is only one optimal button with a slightly higher average reward. Okay, right? And you can actually set this P parameter here to control the setup in a way that if P is greater than 0.5, then the optimal arm will have the lowest aleatory variance. So why this setup is interesting, right? Because most of the case in the bandit setup, you are interested in exploration-exploitation trade-off. And exploration means you need to measure uncertainty. One way you can think about it is to measure the total uncertainty, which means you don't need to do the competition. But if you have a different aleatory variance, then the extended uncertainty there will be more useful. So let's talk about the algorithm. So this is just a reminder for you for the very classical bandit method UCB. Okay, so UCB upper confidence bound works like this. You need to maintain a model for the estimate for the mean reward as well as the some kind of variance or standard deviation of the reward for each of the action or for each of the arms. And then during each time, you're going to select an action by maximizing this interesting acquisition function that is the mean reward plus some scaled version of the standard deviation. Okay, based on that action, the environment will give you a random reward, something from some kind of underlying ground truth. Okay, once you've observed this new reward, you're going to add that into your data set and then update your model's estimate for each arm's mean reward and its standard deviation. And then you repeat the whole process. Okay, right? So now the interesting question here is you can ask what kind of model are you going to use for this UCB algorithm, right? So here's our results, right? Okay, so let me explain a bit about this. So UCB or UCB1 data, they are basically just the usual count-based model. Okay, you just because you have binary rewards. Okay, Greedy means you don't do any exploration. You start some random pause at the beginning and then later on just start exploiting. Okay? Instruction baseline, that was essentially what I talked about before. In this newspaper, you just directly ask the language model, what is the next arm I'm going to pull? Okay? So other methods like EBTV, they are essentially this UCB algorithm based on the language model's estimate for the mean and the variance. And in particular, TV stands for total variance, which means you don't do our decomposition. EB means epistemic variance, which means you try our decomposition. Okay? So overall, I think first of all, the result says you need to run UCD, okay, style algorithm in here. And second thing here is when in this kind of p equals to 0.7 setting, which means in this case you have lower editorial variance for the optimal arm, the EV method actually works significantly better, okay, than other methods. So here the result is measured by this regret, mean regret as well as the mean worst case regret. Okay, so I can show you one example of the behavior for these arms. Okay, so here we are plotting essentially the number of polls for each of the arms during the trials, right? So what you should expect in a bandit setup, if your bandit algorithm is working, is you will start pulling all of the arms, and then at some point, the algorithm will figure out, oh, which one is the optimal arm, and then later on, we'll try to only pull that particular optimal arm, right? So if you look at this particular example, right? So if you use the EV method, the optimal arm here in orange, okay, it is definitely being pulled most of times. Although the method is not perfect because you can still see that, okay, so it still pulls some other arms, especially this arm. But if you look at this particular trial for the one using the total uncertainty, right? So somehow this trial actually failed because it stopped pulling the optimal arm and then start to pull some other arms. So this is also reflected by the higher regret. And if you look at essentially this estimate, right? So the epistemic uncertainty estimate here is that actually going down, right? When you collect more and more data points, which is as expected, and you actually want this uncertainty to shrink in order to start the exploitation mode. But the total uncertainty estimate here, they don't actually shrink that lot. Okay. Yeah, I think I'm done. Okay, so takeaway here is, okay, so we have 3-stage pipeline for language models. We can apply basic methods there. They have different ideas. Okay, here we just try one interesting idea for this in-context learning, and we claim that in-context learning with language model can be made approximately Bayesian. Okay, and once you believe it is Bayesian, then we can start trying to think about estimating the qualities, especially uncertainty quantities that we're interested in. And then we here provide a one approach based on prompting to do that. Okay, we have been trying to explore various directions for future work. So I'm happy to talk about it offline. Yeah, thank you very much.
Are there any questions?
What happens to the uncertainty plots if we don't satisfy C1 and C2 like and calculations?
Yes. We actually tried removing the implementation. Okay. Obviously, our implementation needs a lot of compute. So it still works to a certain degree, but the plot result, qualitatively speaking, is worse than the result I show you. I mean, so one drawback for us is essentially we don't know actually how to do the quantitative test, apart from doing model checking, right? But the model checking here also requires you to improve essentially the accuracy, okay? And the total uncertainty behavior, which is something that we are actively investigating.
And what about C2? Like where you don't check for the marking error requirement.
Oh, yes. So I actually have one slide for that. Okay, I don't have time to talk about that before, but I do have one slide for that. Okay, Yeah. So you can actually say that, okay, I can try to repeat, right, the question as I mentioned before, right? And repeating the question, you can see that that is in this gray curve. It actually works to some degree, okay? But the KL divergence there is actually much higher. So this actually is in log scale, the y-axis, okay? The KL divergence here for this repeated strategy is actually much higher than other methods. So because we don't have ground truth, okay, it's very difficult for us to tell, which one is better, quantitatively speaking. But our recommendation here is that if you want to claim your estimate being Bayesian, you should try to satisfy those kind of conditions as much as possible, modulo computational constraints.
I'm sure the non-Bayesians would ask, like, if you just bootstrapped.
Yeah.
Did you prepare that already, or?
Not really. Okay. I mean, our purpose for this work is purely we are just purely interested in this setup. If language model is doing some Bayesian stuff, or if there is a way to make language model doing some Bayesian stuff, can we actually compute uncertainty transition? That is the main question that we're interested in. This work, we are not excluding other ideas saying, if you don't like Bayesian paradigm, you do some non-Bayesian methods, non-Bayesian estimation methods, right? Or if you don't want to put in some kind of efforts to ensure this, exchangeability or promote exchangeability, then I think you can still compute it, but some kind of theoretical property will be lost. For example, the multi-tail property is one thing very key, the consistency requirement for Bayesian inference. If you throw that away, my hunch is that there still exists local beliefs, okay, that is updating sequentially, but those local beliefs, they are not updated in a consistent way, okay?
Yeah. I think what would be interesting to see that if you were to ask certain questions, then the certain questions first, then the answer is completely garbage.
Yeah.
Right?
Yeah.
And that would make sense because you say, if you want these kind of situations to not happen, then you should be seeing things in certain ways, So I think that would be interesting where that, as you say, like if it's not Bayesian, then making it Bayesian.
Oh yeah, okay.
And I don't know if that's possible, but I could definitely see how to break it.
Yeah, for sure, yeah.
I don't know how to correct it.
With one question on Zoom. The question is, how large the ensemble needs to be to ensure approximate Bayesian behavior?
Oh, okay. I think in our case, so for permutation, I think, okay, so for example, in this classification example, we have, I think 20, okay? We tried 10 permutations, okay? I mean, we also tried to increase the permutations, but it seems that 10 permutations and then later on sampled 10, 5 to 10, these possible answers skew is empirically speaking enough, okay? So obviously, if you want to do more, then you can, right? But it's very expensive procedure. We need to admit that.
Okay, I hope this answers the question. Any other questions? I think there were already a lot of questions during the talk. So yeah, thanks for the answer from Zoom. So
Yeah. Thanks for the questions. Yeah.
okay, then let's thank Yingzhen again for the great talk.